Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry the Mystery of Molecules after a long time. Okay, so today we shall discuss homoaromaticity. This homoaromaticity is a very confusing topic for many students. So today I shall try to neutralize all of your doubts and I'll provide lots of examples such that the concept will be completely clear to you. So let's start. But before going to the details, one MCQ. What is the major product of these reactions, student? I request everyone, please pause the video, read the question carefully, try by yourself, and whatever answer you get, please write in the comment box. Do not hesitate whether your answer will be right or wrong. Don't worry, at the end of this discussion, you will have the right answer with explanation. Now, let's go to our main topic. Now, before going to homoaromaticity, we should know a little bit about COT or cyclooctatetraene, about the chemical property of this molecule. Means it is aromatic or non-aromatic or it is anti-aromatic according to Hückel rule. So let's learn a little bit about the Hückel rule. What is Hückel rule for aromaticity? So condition for this Hückel rule, the points are: the compound must be cyclic, compound must be planar, and each atom must have one p orbital and they are in conjugation. Obviously this conjugation possible when they are in the same plane. And the fourth point, if they have 4n plus 2 number of pi electron, it will result aromaticity, means the compound will have stability. And if it has 4n pi electrons, it result anti-aromaticity, or you can consider this compound have instability. This is the main thing. So based on this, generally people conclude cyclooctatetraene is anti-aromatic. Why? By the way, look at the drawing strategy for COT. Okay, alternatively double bond. So if people look at this, they'll say, okay, cyclic, planar, conjugated, 4n pi electrons, it's anti-aromatic, unstable. Remember, molecule doesn't like instability or anti-aromaticity. What they do, they try to devoid this anti-aromaticity by giving up the planar arrangement. And actually this COT molecule looks like this. So you can understand that all p orbitals not in the same plane. So compound is not the planar and conjugation is not possible here. That means it is a non-aromatic molecule. It's a very important information. Now this much we understand. But if you take this COT and if you treat it with metallic potassium in anhydrous THF, what it happens? This COT accept 2 electron. Why? Because potassium is a group 1 element, very electropositive. So it releases electron and be K plus. In this way it have nearest noble gas argon's electronic configuration. Now 2 potassium releases 2 electron and those 2 electrons are accepted by this COT molecule. Question: why? What is the driving force? Because driving force is aromaticity. Now previously it has 8 pi electrons. To each double bond contributes 2 pi electron. Now after accepting this extra 2 electron, it has total 10 pi electrons. Means according to the Hückel rule, I mean 4n plus 2 rule, here n is equal to 2, so aromatic stable. So that's why this dianion is produced. Not only that, if you take an oxidizing agent, then what happened? It gives up 2 electron and produce this dication. Why? Because this dication has 6 pi electron. If you put n is equal to 1, so it's a Hückel rule, means relatively stable. So that's why COT shows such kind of chemical behavior. But if you treat this COT with acid, very strong acid like concentrated sulfuric acid or superacid, then protonation takes place. Previously I told these double bonds are not in conjugation. So you can consider these double bonds as isolated alkene. So isolated alkene can undergo protonation, means any one of these double bond will be protonated. Now this H plus means neutral molecule plus H plus, so it will be a cationic. Now this carbon form a bond with hydrogen. Fine. By the way, previously each carbon atom has one hydrogen. But from this carbon atom, the double bond goes, so there is a positive charge. Positive charge means deficiency of electron. Now previously what was the problem with COT? 8 pi electron. But right now if you look at 2 to 6 pi electron, so it can have aromaticity. But still one confusion, that there is one sp3 carbon. So actually what they do, they bypass this sp3 carbon. But so each from here, if you look at 1 2 3 4 5 6 7, now in carbon number 7 there is a positive charge. Positive charge means deficiency of electron, but still cation means it has a p orbital, sp2 hybridized, so they can undergo conjugation and result some kind of stabilization. Question, how? So you can see the carbon number 1 and carbon number 7, they are pretty closer. So in three-dimensional space, this p orbital can overlap, and this is the basis of homoaromaticity. Actually, when scientists does protonation on this molecule, they observe that this molecule has a very unique stability. They were confused. Later on they found out why this is stable. Actually, if you look at from carbon number 1 to 7, so this is 1 2 3 4 5 6 7, so all have p orbital and they can undergo conjugation. Actually, this is the definition of aromaticity. If you look at benzene, in benzene all carbon has p orbital and they are in conjugation. Now these group, you can see this is outside. By the way, you can see, sir, this proton is inside. Yes, you will have some unique property or differentiation between these two protons. I'll come after some time. So this is the basis of homoaromaticity. The reason behind the exceptional stability of this molecule is explained as homoaromaticity, because this is a significantly stable. If you look at the resonance energy for this system, it is 22.8 kilocalorie per mole. But if you look at benzene, which is 36 kilocalorie per mole, significantly closer. Even if you look at the C1 C7 bond distance, significantly closer, 2 angstrom, whereas benzene bond distance 1.39 angstrom. So from there you can understand these carbons are pretty closer, such that overlap possible in three-dimensional space. Now this is proposal. Is there any proof? Yes, NMR. Okay, so NMR will prove the stability of this molecule or existence of homoaromaticity. Now when there is aromaticity, there is a ring current, and because of this ring current, shielding and deshielding zone produced. Now I told this proton, actually drawing is not perfect here. You can clearly see this is inside this zone. So consequently its chemical shift value is minus 0.73. It's minus, and look at here, it's a 5.86. How possible? If you normally think based on your common sense, both are attached to this carbon, sp3 hybridized carbon. So why this is so much high? Because it is not attached to any electron withdrawing group. And why this is very low? Because of this ring current. So this proves that this homotropylium ion having aromaticity or aromatic character. Now not only finished here, further proof. If you form a complex of this homotropylium cation with molybdenum tricarbonyl, obviously this is the homotropylium cation. So these molecule coordinates with benzene type system or aromatic systems. So now when it coordinates, the aromatic character retains. So look at the value, still this minus 0.15, previously minus 0.73, closer. But if you look at iron tricarbonyl, it prefers to coordinate with a diene. So when it coordinates, this diene character maintains. See, this delocalization sign is given here, but here it is not given. So actually it's a diene, cation positive charge diene. So that time look at the peak position 1.35, 1.53. Means this behavior looks like typical sp3 carbon chemical shift value. So this clearly proves that okay, this molecule has the homoaromatic character, actually aromatic character, and this aromatic character is named as homoaromaticity, proved by NMR spectroscopy. Now if you look at simple tropylium cation, it is actually a C7 aromatic cation, and here 6 pi electron exists. Similarly, if you look at homotropylium cation, It is actually a C8 because there is one carbon extra, and it also has 6 pi electrons. So there is a similarity. Now next, some other examples like homocyclopropynyl cation. So if you take this is cyclobutene ring attached to this OAC, and if you treat it with superacid. Now what is superacid? Remember, superacid means they are very strong acid. Yes student, they are very strong acid. Technically, if I say they are stronger than concentrated sulfuric acid or pure sulfuric acid, like perchloric acid, antimony pentafluoride, HF, like that. I have already made dedicated lecture on it. Please visit if you are interested to know about this. It is a very interesting molecule. Now superacid, from the name you understand, very strong acid. So if I say very strong acid, the term indicates okay, it will release H plus very efficiently. Yes student, they are so much powerful that they can protonate even hydrocarbon also. Now what happens in the next? Next, this H plus protonates this OAC, this oxygen atom. Why? Because this oxygen is electron rich, it has 2 lone pair. By the way, you can say, sir, instead of OAC, we know resonance happens and this carbonyl oxygen is more electron rich. Agree? Okay, do protonation here. For your satisfaction, let me accept. This is OH, this is CH3. Fine. So they are protonation, but still it means that this is carrying a positive charge. Consequently, what happens after having this H plus addition? This leaves. Why it leaves? Because this part is carrying a positive charge, and positive charge on oxygen atom here or here, whatever you consider, not that much stable. So it leaves and produces this cation. Now remember, a carbocation's production is dependent on its stability. Now why it is produced? Because it has some stability. How? Look at this is, for example, let's name it 1, 2, 3. So all 1, 2 and 3, they are sp2 hybridized. Each of them have p orbital, and if you look at, there is 2 pi electron, I mean this double bond. So if you put this through 4n plus 2, I mean n equal to 0, so it's like okay sir, possible 2 pi electron. And now if you look at here, this is a CH2 sp3 hybridized. How it is stabilized? So these 1, 2 and 3, they conjugate together and form a 3-member ring. So you can expect there is one p orbital, there is one p orbital, there is one p orbital, and these p orbitals are in conjugation like this, delocalization, and this delocalization means stabilization, and it is outside this CH2. So this is actually, this cyclobutynyl cation could be considered as homocyclopropynyl cation, because we know this cyclopropynyl cation is aromatic in nature, where this n value is equal to 0. I have already made many lectures regarding such kind of thing. Even I have made a dedicated lecture on cyclopropynyl cation. Please visit for further learning. Now let's go to the next example. Next example is, this is actually a 3-member ring formation. Now you may think, sir, how you can prepare? So you can take this cot molecule and you can make this 3-member ring. For example, carbene addition, like that you can make it. Now cot has a problem because of its 8 pi electron, but after this 3-member ring formation, it is gone. Now if you look at here, 1 double bond, 1 double bond, 1 double bond. Now if you give superacid, very strong acid, they will release H plus, and that H plus will protonate. Now question, where they will protonate? If you look at this molecule, 2 types of bond exist. One is pi bond, another is sigma bond. Now pi bonds, the electron density are loosely bound, lumpy, so that could be protonated easily. Now if you look at, in this molecule, there are 2 types of pi bond, 1 type, 2 type. Now question, where the protonation will take place? If you protonate this pi bond, so protonation will happen, but it will not result significant stability. Why? These 2 double bond became isolated. But if you protonate in double bond 1, it has some stability. Now you can expect, okay sir, this position, if I protonate, then you will get this one. By the way, there were 1 proton previously, so 2 protons. This is the cation. It is expected to be more stable. Why? Because it is allylic type, means in conjugation with these 2 bonds. So more stable, generally you expect. And if you look at this another position, if the protonation happens here, then this is hydrogen. Now generally it is expected to be less stable. Why? Because it's a isolated secondary cation, carbocation. Previously it was also secondary cation, but it is a conjugated, okay, conjugated secondary carbocation, so more stable. But if you look at the actual proof, this B is more stable. Question why? So you can see here, these B have homoaromaticity. How? So here you can see this part behaves like CH2, this part behaves like CH2. But there will be a question that, sir, it's a sigma bond or pi bond. I am talking this bond. Is it a sigma bond or pi bond? For that purpose, you need to understand little bit about the chemistry of three-member ring. So this three-member ring cyclopropane. So here each carbon is sp3 hybridized. Now if I say sp3 hybridized, so ideal bond angle associated with sp3 hybridization is 109.5 degree. But if you look at here, there actually bond angle is lesser, closer to 60. So there will be a severe bond strain. Now if you look at the bond angle value, sp hybridization bond angle 180 degree, sp2 120 degree, sp3 109. So if you increase p character, bond angle value reduces. Now what this molecule does, this increases p character in this bond. Yes, it increases more p character in this bond, consequently more s character used in these carbon hydrogen bonds, and it results a banana bond. It's not a direct pure sigma bond, it's a banana bond, like bent overlap type of thing. So you may consider like this kind of overlap. Okay, now what happens in the next? So it uses more p character such that it can reduce the angle strain, because more p character, bond angle is, angle strain less. That is the thing. Now that's why you can consider this bond is not that much stronger like this sigma bond. Okay, so it has a partial p character or p orbital overlap type of thing. Now when such kind of aromatic stabilization possible, when there is an opportunity, then molecule adjusted itself such a way that this bond doesn't behave like a sigma bond, it behaves like a overlap of 2p orbital, parallel or sidewise overlap. So in that case, now look at this bond I am talking, this blue bond, it is. So it is this overlap. And next, this is a positive charge, this is the positive charge means vacant p orbital, and rest of these two, this one pi bond here, another pi bond here. So total how many pi electrons? Look at 2 pi electron, and this bond pair behaves as a 2 pi electrons. So total 6 pi electron is in conjugation, obviously, and one positive charge is there. So because of these resonance or delocalization, this positive charge is delocalized and stabilized. So I can conclude that B is more stable because of this homoaromaticity, which is not available for option A. Now let's go to the next example. Is homoaromaticity could be observed in anion? Actually there is a lots of debate. Now look at this example. If you look at these two example, just difference is the double bond. Now here pK 31.4, where pK 40.5. Very high difference. Question why? So this phenomena could be explained on the basis of homoaromaticity. How? Now I am talking about the pK of this proton. If I am talking about the acidity, then you need to think about the stability of conjugate base, means whatever space is remaining after the removal of proton. Now when you remove this proton, there is a negative charge. These negative charge remain in the p orbital, because in this way it can undergo conjugation with this double bond. Because if I look at, this is actually allylic proton. Now allylic carbon ions are in resonance with the double bond. Fine. Now if you look at in this case, I'm talking about this A case, the carbon ion can have a delocalization like this. Now you may think, sir, possible there is one carbon in between. Yes, I agree there is one carbon in between, but such kind of overlap possible in space. three-dimensional space, these p orbitals are not far away, they are significantly closer, and that is the reason these negative charge is delocalized over all 5 p orbitals. Means delocalized means stabilized, and that is reflected by this data. Stabilization of the anion by 12.2 kilocalorie per mole energy compared to the anion of B. Normally this much amount of stability is not observed. So this proves, student, that homoaromaticity exists, and homoaromaticity is responsible for the higher acidity of this molecule. So in conclusion, whatever you have learned, that homoaromaticity is a exception of Hückel rule because one sp3 or more than one sp3 carbon exists, and in this case the overlap of orbital takes place, I mean obviously p orbitals, by bypassing the sp3 carbon atom belonging to the ring. And the next point is the close proximity of the p orbital is actually responsible for such kind of overlap in a three-dimensional region, and these homoaromaticity could be proved very well by NMR spectroscopy, because aromaticity means ring current, and ring current could be showed by the proton's position. Okay, so this is the overall discussion. Now let's go back to our MCQ. What is the major product of this reaction? So actually in this reaction 4 molecules of acetylene reacted together and produces this cyclooctatetraene. This is a one-step preparation of this quat molecule. Very interesting as well as important information. So I suggest student, please remember this information. Okay, so this is the overall discussion. I believe this video may be useful. Thanks for watching, and if you really consider the content of my channel is worthy, then please help this channel to grow. So see you in my next video. Bye bye.